is going to be 2443 pounds to the right, 4232 pounds upward, 443 pounds to the left, and 768 pounds up. But again, even if my only purpose was to find the support reactions, I still had to go through some of this internal stuff until I got down to at least one of the support reactions. And then I could have used the overall equilibrium to get the other support reaction, EX. But we have more external support reactions than are normally needed to make up for the lack of internal rigidity. The fact that the internal structure is not rigid once it's removed from its support. So that's the method of joints for solving trusses. Any questions on method of joints? Going to show you another method for solving these trusses, which is sometimes convenient. And this is going to be called the method of sections. First off, I want to talk just briefly about two-force members again. Two-force members, and all of these members that make up trusses are two-force members. In a two-force member, the forces have to be along the line joining the points where the two forces are applied. That would be true even if the member wasn't straight. The forces would still have to be equal magnitude, opposite direction along the line where the two forces are applied. But for a straight two-force member, if I cut the member at some location and ask, what are the internal forces at that location?
How much is it?
Well, we're going to get to that in
I've seen one for like $100.
the next chapter, I think it is. We're going to talk in detail about what these internal forces are, but you might imagine that there are forces between the atoms of the part that I took away on the atoms of the part that I kept. However complex those forces are, we know that we can replace that with an equivalent force couple. Any system of forces can be replaced with an equivalent force couple, acting at some appropriate point. So I'm going to divide that force into horizontal, vertical components. Actually, it's normal and tangential to the surface. And a bending moment. But for the straight two-force member, when I sum forces in the x direction, I get that the axial component of force is P, not zero, it's equal to the force at the end. When I sum forces in the transverse direction, I get that V is equal to 0. And when I sum moments about a point on the end, the point where that equivalent force couple acts, the P has no moment, the V has no moment, the T has no moment. The only thing that has a moment is M, and therefore M has to be equal to 0.
You stop.
That does not work if I think of a two-force member that's not straight. In this case, we will get both tangential and normal components, and we will get a moment. So what I'm talking about is peculiar to, special to these straight two-force members.
Oh, maybe.
For a straight two-force member, the force at each and every point within the member is the same as the force applied to the end. So whether I think of the force at that location or this location, or wherever I think of the force at every one of those sections is equal and opposite to the force at the end. What that means is, when I have a more complex structure, I can cut through the members of the structure, and the forces in the members where I cut through are still going to be along the member. So If I'm only interested in the forces at a few points along the member, or a few members within the truss, instead of going joint by joint all the way through this truss, finding the force in every member, if I'm only interested in one or two forces, it might be quicker to just cut through the members and treat it as a rigid body rather than to take it all apart into its tiniest little pieces. So that's going to be the method of sections, and I'll use this problem to illustrate how I would go about doing that. Here I'm only interested in one force. Why? I have no idea. It might be that for some reason I think that that's the critical member in the truss, that's the one most likely to break. More likely, I dumped all of this into a computer program, and these trusses are very, very easy to solve with a computer program using the method of joints. You put in XY coordinates for all of the joints, you say which joints are connected, you say which joints have loads applied to them, which joints have supports, and you tell the computer to go to work, and it spits it all out. Now, if you believe computers, that's the end of the problem. I don't believe computers. I love them dearly, but I don't believe in anything that I can't check. So unless I can verify somehow, at least get an idea that it looks like the right answer, I don't believe it. I've had too many cases where the computer told me the wrong answer. Computer Center says it's not the computer's fault, it was the guy who programmed it, but that makes no difference. It's still a wrong answer. And you need to have some way of finding out, is the computer giving you the right answer or not? So even though the computer can spit these out very easily, it's nice to have a quick way of checking one or two or three members and making sure that what you're getting out is reasonable and what would be expected in that situation. So anyway, we're interested in the force in member DG in this truss, which has kind of a weird shape. We've got loads. There are 5 loads applied across the top. They're all equal, not told numbers. We're just doing everything in terms of this symbol L. There is a pin at B, provides whatever force is needed in whatever direction is needed. Show that in terms of its components. There is a roller support at A, which can provide only a vertical support. Offers no resistance to movement in the horizontal direction. Whether this is a solid panel or made up of pieces is immaterial as far as overall equilibrium is concerned. All that matters is that the points don't move relative to each other, and these are the places where loads are applied. So if I do overall equilibrium on this, the only force in the horizontal direction is B, X. It's going to be 0. Some forces in the vertical direction, I get AY minus BY. And I don't have enough loads on there. There's supposed to be another one in here. There's supposed to be 5 gaps. It says 5 panels. So there are 5 gaps, but there are actually 6 loads going across there. So it's minus 6L equals 0. But that has 2 unknowns. Given L, AY, BY, both unknown. So I'm going to have to take moles.